Okay. So the first thing that you need to notice in design specifications is that the design specification will all at least in time domain. So root locus design is also called time domain design because you're designing in time domain, right? Whereas Bode plot design or Nyquist plot design are called design and frequency domain because you'll be drawing frequency plots, okay, sinusoidal response. This terminology is first clear.
Sorry, sir. Could you come again, please?
So root locus design is called design in time domain, okay, because the specifications are in the time domain, like peak, overshoot, settling time, and all those things, okay. Whereas design using Bode plot or Nyquist plot, which we'll be studying in next week or following weeks, it is called design and frequency domain because you're studying the frequency response using Bode or Nyquist plot, and frequency response is basically sinusoidal input response. Okay, that is why they are called frequency domain design. Got it? Is it
Yes,
clear?
sir.
Just a name.
Yes, sir.
Yes, sir.
So in root locus design, what will be specified is transient. There are two types of specification. One is transient response specification. The other is steady state response specification. The transient response specification will be a peak, overshoot, and settling time, as usual. You learned the second order systems. Do you remember? Sorry, it's hanged up. Do you remember?
Yes, sir.
And the steady state error will be in terms of the steady state error constants Ka, Kp, Kv. Do you remember those three?
Yes, sir.
So
Yes.
if it is type 0, it is Kp. If it is type 1, it is Kv. If it is type 2, it is Ka, right? So those either of these three will be the steady state. If you give the steady state error, you can translate that into Kp, Kv, Ka specification. Okay, either of them. Okay, so there are two transient response specifications: the peak, overshoot, and settling time, and there is a steady state error specification. Okay. Now the thing is, you have studied time response specification only for second order systems, correct? Up to second order. For orders 3 and 4 and all, it is very complicated to derive elegant solutions to differential equations using Laplace or whatever. So what we do is we assume that the system is second order, okay? So, and then we assume that there are only two poles. We assume that the other poles are very very far away, so that they don't alter the design specification that much. Do you get the logic?
Yes, sir.
Sir, this is also another question I had. So, for
Yeah.
example, you have this function g of s equals to k upon s into s plus 1 into s plus 2, right?
Mm, mm,
What we can see on the screen itself.
mm.
So, here we'll only be considering the poles that are near to the origin, right? For example, s and s
No, no,
plus
no.
1.
See, here the poles are zero, minus one, minus two. There is no dominant pole here, correct? All three of them are pretty close to the origin. What I am
Okay,
saying is, for the closed loop system, you will want to have two poles close to much closer to the origin than the third.
right.
Got it?
But still, much closer. I mean, a pole being
If
closer or far
five
away.
times or 10 times closer is pretty
Okay.
much a thumb
Right.
rule. There is no specific.
All right.
It's okay. The more far away it is, the more accurate your design specification will be satisfied. It's not a binary thing. Okay, close and far are not binary things. The more closer it is, the more screwed up your results will be, and the more far away the non-dominant poles are from your dominant poles, the more accurately your design specification will be satisfied. Okay, as a thumb rule, 5 or 10 times the distance. Okay, you can keep that. Now let's consider this system. G of s is k by s into s plus 1 into s plus 2. So here the k is the only single variable varying parameter, design parameter. So you will obviously use the root locus. Now, what you have here is these turn out to be the closed loop dominant poles. So they are stable because they are on the left half of the S plane. Okay. And now they are saying a slight increase of gain k to 6 results in poles which are here now, which makes it unstable. So if you choose k equal to 5, you get stable. But suppose your system is kind of parameters are slightly changing, the gain is slightly changing due to stuff getting heating up. Then if the gain changes to 6, that's it, you're gone. So the system is not very sensitive to changes in gain. So that is where the concept of gain margin comes. Okay. So when k equal to 5, the gain margin is not very high for the system because even a slight change, 5 to 6 makes your system go unstable. Got it?
Yes, sir.
So whereas if you put k equal to 1, the dominant poles are here, and then with the system, it is more tolerant to changes in gain now. Okay, even with gain 5, gain from 1 to 5 is a 5-fold increase. Even with a 5-fold increase in gain, system is still stable. Whereas compared to here, when k equal to 5 changes to k equal to 6, it is changing only by a small ratio, which is 6 by 5, which is 1.1 so something. So this gain margin of this at value here is high. K equal to 1 is high. Got it? And then some import. So you see here, this sketch, do you see? So these two are the dominant poles, and the other poles, they are not that far, but still far away enough so that the design specifications will be satisfied for these two, considering only these two pairs of poles. So what happens is that I told you, right? A canonical thumb rule is the other poles and zeros should be at least 5 times far. Okay. So the real part of the other pole should be at least 5 times far away compared to the real part of the dominant poles. Do you get it? Do you get this?
Yes, sir.
Yeah. So now you have, as usual, this is the GFS is the plant and GC is the controller. We want to design GC such that the closed loop system satisfies the design specifications despite, and it has a nice margin even though there may be changes in GFS. So the first step that you have to do is translate this. So the poles of a second order system in terms of zeta and omega n are given by this formula. This you remember, right? Solving the characteristic equations in the previous unit when we saw in the beginning. This you remember, right? Correct? Okay, if you don't say anything, I'll just assume you remember this. So these are the formulae for the peak overshoot and the time settling time. Okay. So now the thing is, you have to translate these specifications on MP and TS to specifications on zeta and omega n, or more concretely to specifications in the pole location. You have to see, you have to see where all the poles can be located depending on the constraints on MP and the constraints on TS. Okay. So for example, let us say you want uh, you know so when zeta is constant, what happens? So take this formula. So in this formula, the radius, the magnitude of, what is the magnitude of this complex number, pa? Tell me here. What is the magnitude of the
Uh,
complex number?
Under root zeta omega n whole square omega root 1 minus zeta square whole square.
If you simplify everything, what do you get? When you work out on your
It
notebook and tell me,
Yes, sir.
you'll find stuff cancels. So when you square the real part, you'll get a zeta square here. When you square the imaginary part, you'll get a 1 minus
Yeah,
zeta square here.
it will get omega square.
Yeah, so it will just simply, if you take the square root, if you take square and take the square root, you'll simply get omega n, right?
right, omega n.
So the magnitude of the complex number is nothing but the radius, so distance from the origin, correct? So if given omega n equal to constant means the magnitude is fixed. Okay, got it. So fixing omega n is same as fixing the radius of this complex number from the origin. Okay, fixing omega n is same as fixing the distance from the origin. Do you get this? Do
Yes,
you
sir.
get this part? And
Yes,
fixing, yeah. Please ask. Don't
and
feel
I'm
shy.
assuming
Ask.
you are saying fixing zeta is same as fixing the angle because
Exactly.
sine is
That's what
same
I'm
but
coming next.
right, right, right.
So if you take the argument of this complex number, treat this as the imaginary part, treat this as a real part. Tan theta is imaginary by real, right? So when you take the argument, the omega n cancel, right? When you take tan of this, so theta is tan inverse something, right? So the angle from the origin depends only on zeta, correct?
Yes, sir.
So an angle fixing zeta is same as fixing the angle of the pole with respect to the origin. Okay,
Yes, sir.
and so if somebody gives you ranges, theta is between this and this, omega and between this and this, they are equivalent to fixing this. I don't know what exactly calls the name. I forgot. I think. Okay, you'll have this region. Do you see it? Can you visualize this?
Yes, sir.
And how about fixing MP and TS? Okay, so MP depends only on zeta, right? So fixing MP is again same as fixing the angle only, correct? MP depends only on zeta. So for a
Yes,
given
sir.
given MP translates to a given zeta. So fixing MP is also same as fixing the zeta, which is same as fixing the angle, correct?
Yes,
That
sir.
is what
Correct.
the orange part shows. It's angular thing. But fixing settling time, what is settling time? It depends on zeta into omega n, right?
Yes, sir.
What is zeta into omega n?
It is it is omega d, I think.
Is the
No, it
real
is the
part,
real
I think.
part. It is the
The
real
real
part.
part.
It is the real.
So fixing the settling time is same as fixing the real part. So the rectangular region you get. In the rectangular region, the real part is grid, in between two numbers. Correct, you see?
Yes, sir.
So the thing is, based on the time response specifications that you have, you first translate them into the allowed pole locations. Okay. If somebody tells you, the settling time should be between this and this, and the zeta should be between this and this, it will be the intersection of these two regions. One is this triangular, infinite triangle, and the rectangle, right? So this trapezium it will be the allowable pole location. Got it? So the first step in root locus design is fixing the locations allowable range of the dominant poles. Okay. Is this clear?
Yes, sir.
Okay. Next is the steady state response specification. Keep that in mind. If it is zeroth order, the step response steady state error is 1 by 1 plus kp. The ramp response steady state error for type 1 system is 1 by kv, and parabolic error for type 2 system is 1 by ka. Anything above will be infinity, anything below them will be zero. Okay. So now let's start with a simple example. Consider a system like this type 1 system 1 by s into s plus 2 into s plus 4. Here what they are saying is design a controller such that the closed loop system has an overshoot less than 16% and a settling time less than 6 seconds. Does a simple proportional controller solve this problem? Okay. So if a simple proportional controller indeed solves this problem, then you can use root locus, because root locus is basically finding out how the where the closed loop poles go given a but given gain, right? Some gain, pure gain, right? So pure
Yes,
gain is
sir.
nothing but a P controller. So first what we do is translate these two specifications into uh, pole locations, dominant pole locations. Okay. So find some dominant pole location satisfying these two criteria. Okay. These two. So it turns out these two are the open loop pole locations. Wait, one second. So here they are showing the time response, step response. Okay, so here the orange part is assuming that only the dominant poles are there, no other pole is there. Okay, the blue part is basically plotting the actual time response, taking into account the other pole that has been ignored because of the dominance of the dominant poles. And you get what the plot is saying. Do you understand what the plot means? First, I'll explain.
Yes, sir. So it is
Okay.
showing us the it is showing us the peak overshoot and the settling time.
Exactly. So the blue part is the plot of the actual system having all the three poles. Okay. The
Right.
orange part is basically our idealized assumption that there are only dominant poles and you're neglecting completely the third pole. Got
Ah,
it?
okay.
And
Yes, sir. Got it.
the more accurate your design is, the more closer these two will be. The more dominant the poles are, the blue and orange will match, very closely. So what you have here is these. You first draw the root locus, and then you see. It turns out you are lucky in this case that the root locus actually passes through this pole. Got it?
Yes, sir.
The whatever you wanted here, you wanted here, right? This part you said this satisfies these two constraints, and it turns out that if you draw a root locus for this system, it passes through these two poles, 0.668 plus or minus 1.15. Okay, so since the root locus of the system passes through this, it turns out a simple P controller can solve this design problem, because root locus is basically analyze, seeing how the closed loop poles move under a pure P controller, right?
Yes, sir.
Okay, so that is why you see here this. So the answer to this is yes. Can the root locus help us solve this problem? Yes. Got it?
Yes, sir. So, like, how do you came upon this conclusion? So, because this that two roots are passing the origin, that is why that root
The two
locus can
roots.
solve this problem.
Hmm?
The root locus, the roots which are given by the root locus,
Hmm.
and the root locus is passing those two roots minus
See, if
two
the
root
root
two.
locus is passing through the region where your design specifications are satisfied, then a simple P controller can solve this.
Okay, that
That's what it's.
you shown that like that triangle and that trapezoidal region. My roots are lying in that trapezoidal region.
No,
That's what.
here you are not drawing the trapezoidal region. You just happen to find one point in the trapezoidal region that satisfies. This point lies in the trapezoidal region, and then the root locus happens to pass through this point.
Yes, sir. That is what I'm saying.
Mm. So you are lucky here. Okay, the root locus passes through the
But how
trapezoidal
did
region.
we come to this conclusion?
What?
Okay.
Like if you just scroll up once.
Mm.
Yeah, yeah, yeah. So the question is, design a controller such that the closed loop system has an overshoot which is less than 16.1% and settling time of 6 seconds, right?
So assume take these two as take this as a pole location and substitute in this formula for the peak overshoot or settling time and see.
Okay, right. So we'll get the zeta, isn't it?
Of course.
Yeah.
So the
Then
pole
for what?
locations are given using the pole locations you can get zeta on omega n. The magnitude of the complex number is omega n and tan inverse of the argument based on that you can get zeta, right? You get the magnitude of the complex number. So this pole is basically here, this, right? This pole is here, right? So the magnitude of the complex number so will be omega n. Once you find omega n, the real part is zeta omega n, right? So divide the real part by omega n, you'll get zeta, correct? So
Okay, so
once
you're
you once you
so we'll
find
have to.
omega n and zeta, substitute in these two formulas to get settling time and peak overshoot. Got it?
Yes, sir.
These are all whatever we studied in the previous classes. We are applying, we are applying a lot of formulas together. Okay. So the pole location of a second order system is this. So the magnitude of the complex number equate that to omega n because the magnitude of this guy is omega n. So you find the magnitude of this complex number that will give you omega n, and then divide the magnitude of the real part by omega n that will give you zeta because the real part is zeta omega n. And then the settling time will be given by once you find zeta on omega n, this will be the settling time and this will be the peak overshoot. And then you can verify. Got it? So
Done, done. Yes,
if
got it.
the root locus of the original system directly passes through the region of your interest and the remaining non-dominant poles are at least 5 times the distance as the dominant pole, then the simple P controller solves the issue. Got it? If it is not, you have to use a lead compensator or a lag compensator. Got it?
Yes, sir.
Okay, so if the root locus doesn't pass, you have to use a lead or lag compensator. Okay.
Yeah, so exactly now how do we so first of all, what kind of questions can we get in terms of the lead and lag compensator concept? Because I
See,
saw the
you'll
very
obviously not
last
get a
one.
design problem like this because you need a computer to generate the root locus plot, right?
Yeah.
By hand, you can't do root locus accurately unless you manually calculate the pole locations at every k. Correct? You can't get. You can get the rough sketch of the root locus, but you can't get the accurate sketch you needed.
Sir,
So
the thing,
the
these
question
concepts
that you
that
will
you.
get will be testing you on how well you have understood each step. Okay, some Trump's trick question from
Okay.
conceptual question, involving a step or involving like this will be given. Okay,
Okay.
don't worry about the questions right away. Just let this be over, and then we'll see.
Okay, okay, sure.
So the first step is checking if the root locus of the original system passes through the region of specification, and then rendering the other poles much rendering the other poles of less importance, at least 5 times far away from the real part. Okay, so if that is the case, then the proportional controller will solve this problem. Now let's look at this guy, MP less than 10%. Let's say now so far we had MP less than 16% and TS less than something else, if I remember right. So far we had a more relaxed constraint. Settling time could go up to 6 seconds, and peak overshoot can go up to 16.1. Now you're kind of it's a more stringent constraint now. The peak overshoot should be less than 10% compared to 16%. And then TS should be within 5.4 instead of 6 point something. Got it? So
Yes.
you'll get a trapezium for this, and this dominant pole now in the trapezium is this. Again, you choose this based on the draw. After drawing the trapezium, you choose. Okay, got it. Now we ask whether a simple gain adjustment can solve this problem. So again, what you do is you have this minus 0.715 plus j 0.974. So again, you see simple gain adjustment solve this problem. You have to draw the root locus and see. Okay, yourself play with the MATLAB yourself and see if you are. For now, just trust this plot. Can you see this? This is another example. You same logic. Got it?
Yes, sir.
Okay. So this is just a summary. So we first this first slide is all about simple gain adjustment. Okay. So in both cases, simple gain adjustment resulted in the desired closed loop performance specification. In both cases, the root locus passes through the desired closed loop dominant pole locations. And this can be checked directly by the magnitude condition. You can also check this manually also. You'll have 1 plus kg equal to 0, right? Correct? So k will be 1 by g, correct? Minus, correct?
Yes, sir. Correct.
So put your desired pole locations and see whether you get some k. Now,
So you're
your
saying that like we have to put the value of the pole in this location and calculate the K.
yeah, you put the value of the desired pole location and see if the k value you get makes sense. If it is a real positive number, then yes, the root locus passes through that point.
Okay,
Got
okay.
it?
Got it. Yes, sir.
If it is something very nasty or complex number, then it is not. It don't pass through that point. Got it?
Yes, sir. Got it.
Okay. Now you have another specification. MP now less than 20% and TS is now less than 4 seconds, not 6, not 6, not 5, even more stringent. But MP is kind of more relaxed. Okay, 20% you are allowed to go. So what happens now is this is the root locus, and it turns out a simple gain adjustment cannot bring the system to any pole location that you. Here they are just giving a simple example of minus 1 plus j2. But it turns out the root locus avoids this trapezium. No matter whatever you gain you choose, it doesn't pass through. The entire plot doesn't pass through this trapezium region. Can you get it?
Yes, sir. Right.
So because if settling time is 4 seconds, what is the real part? So you get here.
So it is 4 by 16.
Hmm?
4 by 16, which is zeta omega n, right?
Yeah. So for TS is 4 by zeta omega n, right? So what is zeta omega n?
It is 16.
Uh, Wait, sorry. Where was I? So no, this will be minus some. It's minus,
Right.
right?
Minus 4 by 16. Minus 4 by 16.
Minus quarter, right?
Minus quarter.
Okay. TS is 4 by zeta omega n. Here you have TS less than 4. So
Oh,
put
okay. Right.
4. 4 is equal to 4 by zeta omega n. Zeta omega n should be 1, right?
Yes, sir.
So minus 1. Zeta omega n should be minus 1. So it should be at least minus 1, which means get minus 1 or minus 2 or minus 3. But you see, the root locus avoids. The real part never reaches minus 1. Here, do you see that?
Yes, sir. Right.
So a simple gain will not solve this. Got it? So
Correct.
you need to introduce additional poles and zeros so that the root locus actually passes through here. This. Got it?
Yes, sir. Yes, sir.
That is where the idea of compensation comes in. And the philosophy of this is basically the root locus, remember, uh, starts at open loop poles and ends at open loop zeros for infinity, correct?
Yes, sir. Right.
Okay, so we can kind of think that root locus kind of is repelled by poles and attracted by zeros because it tends to end at zeros and diverge from poles, correct?
Yes, sir.
So if you want the root locus to pass to a region, you have to manipulate the poles and zeros so that it passes through. You have to introduce additional poles and zeros so that it passes through the region. Got it?
I think here we should add a zero before
Yeah,
this.
we'll come to that slowly. So that is where the compensation comes in.
Okay.
Um, so effect of adding a zero to the root locus. This is the root locus of the original system. It doesn't pass through -1. I don't know why the scale is. I don't know why the pole marking is left out here, but you see here the same system, right? Now what you do is, I don't know if you can see. I will zoom it. Can you see
Yes, sir. It's
this?
visible. Yes, sir. Visible.
But now what you do is you introduce a zero or -1 now. Okay.
Okay.
It turns out, so you have a zero at -1 here, right? So this kind of, so the root locus branch that starts at this pole will end at here at the 0 -1. Whereas the other two poles, you will get a plot like this. So this will be the modified root locus. Got it?
Yes, sir. Got it.
And now if you choose a pole that are on that dotted line that they have shown, it will be -2.5, correct? Which is
Yes,
much,
sir.
much, it is actually what you want. You wanted at least -1, right? Now you get -2.5, correct? But the thing is, this is not a dominant pole now because the dominant pole there are poles closer than that here. Do you see?
Yes, sir.
Now let's try zero, adding the zero or -3. So it turns out you get this. What are the asymptotes? So asymptotically it reaches -1.5. Do you see?
Yes, sir.
So this is one -1.5 is okay for you. Choose a pole location here, and the other poles, the other third pole will be in this region. Okay. And if you choose far enough k, it will be close. It will be around -4. It will be closer to -4, right? Sorry, it will be closer to -3, right?
Yes, sir.
But -3 is not exactly 4 times -1.5, just 2 times. So again, it's not exactly that dominating. Got it?
This thing I didn't understand.
Do you want
Non
me to
dominant.
go from here or just the third one?
The third one.
Okay, so if you choose k very high, two poles will be at this vertical segment of the root locus where it hits minus
Yes, sir.
1.5, correct?
Yes, sir. Right.
And the
Correct.
third pole will be between -3 and -4, correct?
Okay. 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 I think it is somewhere deriving from the root locus rules only.
Yeah, -3 and -4 is not exactly 4 times -1.5, right? It's
Okay.
not. You need at least five times or 4 times, five times, right? So -3 and -4, even if it okay, even if the k it will be -3 when k is very high because it starts at -4 and ends at -3, right?
Yes, sir.
So if k is very high, it will go close to -3, but -3 is not less exact, just 2 times -1.5, which is not enough to be a dominating pole. So this also fails. Okay. Now this, see here. Now I put a 0 or -5. We get the same plot. Asymptotically it reaches -1.5. But where will now the third closed loop pole be? Where will the third closed loop pole be when k is very high?
It is -4.
Minus 5 starts at minus 4, ends at minus 5. Zero is at minus 5. You zoom and see. Minus 5 is 0 and minus 4 is pole. Minus 4 is always
Yes,
open
sir.
loop pole. So
Right.
minus 5 is very at 4 times minus 1.5, right? If you put the 0 at minus 6 or minus 7, you'll get it. It will be okay. Correct?
Yes, sir. Correct.
So you kind of see that adding a 0 at the right place will satisfy what all you want. The trick is adding a 0 at the right place.
And sir, by the way, the place where this intersects the x-axis is the centroid, right? Which is sum of poles plus sum of zero upon number of poles minus number of zero.
Yeah, okay. Why are you calculating all that? Computer will plot everything, no? Why do you need centroid?
Okay.
I mean,
I
what's your
thought we
point?
can get questions regarding this because there were questions in the practice asking us to plot these, draw these plots. So if we don't have the centroid and if we don't have the angle
See, if using without using computer, you can draw only a rough sketch of the plot. You can get this shape, overall shape you can get. Okay, you can get the overall shape. Okay, got it.
okay, okay, sir.
And of course, the centroid and the asymptote will give you the vertical line that you want. Okay. For simple systems, you can pretty much reason using a rough plot, but as systems become more complex, it screws up.
I think my bad. It's not the centroid. The point where it's intersecting is the breaking point, right?
Yeah, that I can calculate the breakaway point or the breaking
Yeah,
point.
breakaway point, right?
So now adding a zero is nothing but PD control, right? Because wait, you added an extra s plus 5, right? This 5 part is simply P control, right? Whereas the
Yes,
s
sir.
part is derivative control because s is differentiation, correct?
Yes, sir.
So there's actually PD control. You're actually designing PD control here. Got it?
Yes, sir.
So adding an extra zero to the system is actually PD control design. Okay. Now here you can use for a given root locus plot. You can argue using intuition, but
Sir,
yeah.
I mean, I don't know for some reason it's not clicking. Why is it PD control adding a zero?
Okay. If you just add 5, yeah, here I have s plus 5, right? The controller is
Oh,
simply
right,
s
right,
plus
right. Oh,
5.
got it, got it, got it, got it, got it.
The remaining part are already in the open loop system. 1 by s into s plus 2 and s
Yes,
plus 4 is already in the plant. The new
yes.
B
So
coming here is
right,
S plus 5 and the 5 part is P and the S part is D.
perfect, perfect. Yes, got
And
it.
then the root locus is K times S plus 5. K times S plus 5 is a new part. So K times S plus 5 is Ks plus 5K, which is basically a proportional controller with proportional gain 5K and the derivative gain K. Okay. So by root locus
Yes.
basically tells you, how the derivative gain, manipulates the pole locations. Okay, got it. Do you get this or not? I'll be going a little more technical now. So far, we've been dealing with concrete examples. Now I'll be going a little more technical. If
Right.
anything bothering you, just ask me or tell me it's okay. I'll go next. Because if you neither switch on your videos so that I can't see your face, I can't hear you, then how will I know? I'll have no feedback. I will be an open loop teaching. It should be an
Oh,
open
sir,
loop
got
teaching
it,
for me.
got it.
Okay. So now we will give a general procedure for designing uh, PD control or using root locus. So let's say this red colored cross SD is your desired pole location, dominant pole location. Okay, choose that depending on your time response specifications. And obviously omega n will be your magnitude distance from the origin and zeta will be the real part. Okay. Now what you do is the zeros of the PD controller are always real, right? Because it is S plus something, right? A zero PD controller is always, KP plus KDS, correct? So the zero is always some negative real number. S is minus K minus KP by KD. That's a zero, right?
Yes, sir.
So the zero will be somewhere at negative x-axis. Call that minus ZC. Okay.
Yes, sir.
So now what you have to do is choose ZC appropriately so that the root locus actually passes through SD for some value of K. Correct?
Yes, sir.
So for that,
Okay.
what you have to ensure is, at FD, the angle of G and then the angle of GC should add to minus 180 because you get GGC 1 plus KGH equal to minus 1 plus KGH is 1 plus KG is 0, right? Do you want me to write that down or can you understand? 1 plus Kg is 0, right? For the closed loop characteristic equation,
Yes, sir.
correct? So if you send minus 1 to the right hand side, it becomes Kg is minus 1, right?
Yes, sir.
G is equal to minus 1 by
Okay.
K, right? And so the angle of that is minus 180, right?
Yes, sir.
Now, G is the product of the plant transfer function and the compensator S plus ZC transfer function, right? Controller. So G is the product of the transfer function of the plant and the controller. Okay, plant transfer function call it G. The controller transfer function call it GC, which is S plus ZC, the PD part. So now the product of these two is the open loop transfer function, right? Got it? Or should I open a Word document and work it out? Please let me know.
Maybe this is fine
Huh?
for now. For now, I think this will do.
Yeah, so you have that, but if you multiply two complex numbers, their faces add, right?
Yes, sir.
So the angle of GGC is angle of G plus angle of GC.
Yes, sir.
So you want the phase. So if GGC is minus 1 by K, take angle both sides, you get 180 degree, right? Plus or minus 180. But since the angle of GGC is sum of angle of G and sum of angle of G, because arguments add, when you multiply two complex number, the angles add. E power I theta 1 into e power I theta 2 is equal to e power I to theta 1 plus theta 2. So the angles add when you multiply two complex numbers. So what you get is this you get. Correct? Correct?
Yes, sir.
So when you substitute the dominant pole value, you need to have this condition satisfied. Now you know what is angle of G at SD, correct?
Yes, sir.
And you know GC is S plus ZC, right? S plus ZC is the compensator transfer function. See, controller, compensator, these are all different names for the same thing. Amplifiers and electronics people call it compensator because they, and then other people call it controller. PD controller is basically lead compensator, okay, a version of lead compensator, okay. So this is nothing but SD plus ZC, correct? GC is S plus ZC, correct? Understood? Here it was S plus 10, here it was S plus 5, here it is S plus 3, here it is nothing. Okay, so in general it will be S plus something called ZC. The ZC is only here.
So, sir, can we say that a lead compensator is nothing but, as you like just mentioned, you add a PD control to it.
In
That
lead
is basically
compensator, you'll add an extra pole far away from the zero. I'll explain later. Let me finish this. No, don't bother about
okay.
it too much. But this you agree, this is nothing but S plus ZC, right? When you substitute S equal to ST, that you get SD plus ZC, correct?
Yes, sir.
Yeah, yeah.
And this you already know because you know the open loop transfer functions. And then here it is SD plus ZC. So the only thing unknown here is ZC. And based on the equation, you can find ZC. Got it? Because the compensator is K into S plus ZC, right? When you substitute S equal to SD, you get this. So based on that, you can find ZC. Okay, I see some thumbs up. Okay, they are just complicating the notation using theta and phi, but there is a philosophy. Don't get bothered about it too much. This is the basic principle, okay?
So basically, when you add a zero, that will
Hmm.
just contribute to the positive, to a positive factor when it comes to the angle, and that's why it's a lead compensator because it will add an angle.
Yeah.
Okay, perfect.
So based on that, you can find ZC, and then once you find that, by using the magnitude criteria, you can find K. Mod GH is 1 by K, right? Mod G is 1 by K, right? So you can substitute and take the modulus and find K. And then you have to, after doing everything, you have to check that the non-dominant poles are actually far away. The other poles are actually far away, at least 5 times far away. If not, you have to choose some other SD and you have to choose some other SD. Okay, choose some other SD in the trapezium if it is not the case. Got it? Got it? You have to ensure that SD is as close to the origin as possible, and the other poles, closed loop poles at the given K, are as far away from the origin as possible. Is it clear or not?
Yes, sir.
Okay. The open loop transfer function of the compensated system is this. Again, by using the magnitude criteria, you can find K. And this is a final design that they are simulating, and it shows that the design specification are on the requirements. Now coming up, the thing is this transfer function, a pure PD controller, is not physically realizable. I told you, right? Because a pure PD compensator is a high pass filter, correct? I remember telling you this in a previous class. I don't know if you listened or not, or if you came. But a pure derivative is actually two reasons. One is it amplifies high frequency noise, correct? Because take sine omega t, when you differentiate, what do you get? If you differentiate sine omega t, what do you get?
Cos omega. Omega cos.
Yeah, omega cos. When omega is really, really high, what will happen to the magnitude of the derivative? It will blow up, right?
Yes, sir.
So a pure differentiator is very sensitive to high frequency noise. If your system has high frequency noise, any sensor will have high frequency noise. If you work the sensors, you will know. If you plot the reading, you won't get an exact flat curve. It will be haphazard, something, it will be a Gaussian noise. If you see, it will be some fastly changing, very small but still fastly changing noise, correct? Even if that sine omega t is really, really, really small, let's say it is 0.001 sine omega t, even if the magnitude is 0.001, the amplitude is 0.001, if omega is really, really large, it will blow up eventually, correct? So a pure differentiator is not first of all, it is not a physical. First of all, it is dangerous. Okay, it amplifies high frequency noise. The other thing is, it is not physically realizable by any physical system too. People, those if you want an RC circuit or RLC circuit, it's not physically realizable because no system will respond to high frequency noise. Every physical system, when you give fast enough input, it will give up. Okay, so every system, no, there cannot be a high pass filter in theory. In practice, okay, every system will give up after some frequency. That frequency may be really, really high, but it does give up. Okay, so a lead compensator, sorry, a PD controller is not, it's physically realizable, and also it is sensitive to noise. So for that, what you do is you add a pole in addition to the zero, so that this pole, if it is far away compared to the zero, it will not affect the PD. If it will not affect your design criteria, and also it will also kind of make the system physically realizable, because a pole at a very high far away point will act as a low pass filter. Okay, it will not amplify arbitrarily high frequency noise. So now if you do this same design criteria, you will have ZC. You'll have ZC and PC. Apart from ZC, you'll have an extra PC. Do you see here? Hello.
Yes, sir.
So instead of, so the angle of GC at SD is this angle of S plus ZC minus angle S plus PC. Got it?
Yes, sir.
Okay, I think it continues on the next slide. So now you have two design parameters, ZC and PC. And always the pole should be farther to the zero. Otherwise, it will not. You want to implement a PD controller, right? PC is just a physical, just for a namesake. Just for providing some physical realizability. If it is closer to ZC, then it is, you are missing the point. So So what you do is you assume ZC is 1 by T and PC will be 1 by alpha into 1 by T. So you have to ensure that alpha is uh, much, 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 much less than 1. Got it? That's what you want, right? You want alpha to be much, much lesser, so that 1 by alpha will be very, very high and the pole will be very, very farther away from the zero. Alpha is to the ratio of ZC and PC. Got it? So
Yes, sir.
T is the inverse of ZC, which are the units of time, and alpha is the ratio of the zero and pole. You want alpha to be much, much less than 1. Got it?
Yes, sir.
So to design lead compensator, these are the steps. First thing is transform the given time domain specifications to the location of the dominant closed loop poles. That is common, that you did, trapezium region that you did, right? And choosing a point on the trapezium region that you did even for PD controller. And then check if a proportional controller alone meets the design specifications, which means check if just the root locus directly passes through that point of interest. If it does, you don't need any PD controller lag compensator. You can just use that. You can simply use a P controller. Got it? Step one and step two are clear. These are just repeating the previous from the previous. Correct?
Yes.
And then what you do is you calculate the angle deficiency at the desired pole location. Calculate angle at GC of SD. Okay. The thing is, there are several pole zero contributions that. So see, the thing is, you want the angle of G plus angle of GC to add up to 180. Correct? Correct.
Yeah, but shouldn't
So
that
if
be
the,
okay? Negative
so
180.
yeah, if the angle of G already adds up to 180 at the given SD, then you are done. Simple P controller will do. But let's say the angle of G at SD is minus 170. Then you have a 10-degree angle deficit. Okay. So that phi is 10. The angle deficit should be provided by angle GC of SD. So
Sir,
if G
is
is
this
minus
does,
170, GC
does
should
this
be
have
minus 10.
something to do with phase crossover? Because there also we consider GS, GCS, and we equate the angle to
Yeah, it's
negative.
kind of the same. It's kind of related, but let's not confuse. Let's come to frequency response. After quiz two. Okay,
Okay,
you're right, but yeah, I don't want to go off topic now. Okay,
sure.
of course, the time domain and frequency domain are not exactly two entirely different things. They are related. So obviously, there will be a relation between those two viewpoints. But for now, I'm sticking here. So if let's say the angle, you saw already that the angle of, uh, so I'm just using a neutral terminology explaining it to you. So you have this condition, right? This you saw, right?
Yeah,
Correct. So now let's say angle of G at the pole location that you want or desire is already minus 180,
yeah.
which means the root locus already passes through this point even without any GC. So just to find the K value and put that K value. That's it. No need lead controller compensator at all. No need even PD controller lead compensator. Okay. But let us say this is not minus 180. It is minus 170. Okay.
Hmm.
Then this compensator has to provide the extra 10 degrees that needed. The phase lag that is needed.
Correct.
And that is only they are calling it by the name phi. Got it?
Hmm.
That phi is angle deficiency that the compensator has to provide.
Hmm.
But in the case of PD controller, there was no PC. There was only one design parameter ZC. So given a phi, you can find ZC. Okay. But here there are two parameters, ZC and PC. You have more options now.
Okay, okay,
Correct?
okay.
So this is where physically the diagram is given like this. So the angle of the, so let's say phi is the angle deficiency that is shown here. So PC ZC together their angle that is shown here is phi. Wait, I think there is gamma, right? Gamma mu and theta. Okay, just a moment. Uh, So now let's call this angle gamma. Got it? Just look at this diagram once, and they are just naming the angles. They are naming. You can see given ZC, PC, origin, and SD, you can form these two triangles, right?
Yeah,
So they are just giving names to all the angles here.
no issues.
So angle of Z S plus ZC is basically what? What is the angle of this point?
So which point?
what is the angle? What is the argument at s of s plus zc?
Mu1.
Okay, so the you see why I marked this angle as phi, that which is this, correct?
Okay.
So and then now using geometry, you know, using properties of triangles, what you get is ZC is this and PC is this.
Hmm.
Got it?
Right. Okay. Okay.
Now the only problem is there are actually several combinations of gamma and phi that ensures that the root locus passes through the given desired pole locations. Okay. Earlier you had only one design variable, one design parameter. Now you have two design parameters. Okay. In terms
Hmm.
of the angles, here you can call ZC and PC as the design parameters, or in terms of these angles, you can call them gamma and phi. So now, yeah, alpha is ZC by PC. Once again, let me. So here, what they are doing is they are examining how the choice of gamma affect the dominance condition. So, do you remember in the PD controller design, I told you that if you finish designing everything, you have to check that the remaining poles are not are actually non-dominant, right?
Hmm.
And I told you if they are turn out to be if they turn out to be closer to the dominant poles, then you have to it won't work for that given HD, correct? You remember that part?
So which one?
In the previous PD control design, I told you that after doing everything, make the zero pass through this using the PD controller, you have to ensure that simulate and ensure that the other third pole is non-dominant. It's far away from these
Correct.
other
Correct. Correct.
HDs.
Yes. Yes. Yes.
If it is not, you have to choose another HD that is in the trapezium.
Oh, right.
Correct?
Yes.
If you have a specific SD in mind and it doesn't, the poles, it doesn't turn out to be a dominant pole, then you are gone. You have to just give up. Got it? But in the lead compositor, they have an extra design parameter, right? PC. You have two design parameters, so you can tweak to get the dominance that you desire, dominance of the desired pole that you desire. Okay, that's what
Right,
I'm
sir.
trying to say. What? How much time do I have left? What is the time now?
7, 8.
Okay, okay. Yeah, some time. Second. Let me go through this. Oh, sorry, lecture two. So now, what is KV for this system? What are the example? Where do the examples start? Yeah, the original system was this, right?
Yes, sir.
So it is a type 1 system. KV is nothing but multiply S, put S equal to 0. But when you multiply S and put S equal to 0, it turns out KV is nothing but K into ZC by PC. Because here When you multiply by x and put x equal to 0, what do you get? When you multiply by s, the 1 by s and s cancel. The open loop 1 by s and this s cancel. When you put s equal to 0, what do you get? You get an extra zc by pc, right?
Yeah.
In the case of a pure D controller, you won't have, you will get just KD. But here you have ZC by PC. So now you tweak that to have a steady, to control a steady state error. One second. So this is K into ZC by PC. That is your error constant. This is another equation that you have in mind. You have three design parameters. One design, one constraint is provided by steady state error specification. Another constraint is provided by the transient SD. The root local should pass through SD. That gives you one more constraint. And then what you do is uh, for low values of alpha, which will translate to low values of gamma. You if you choose a gamma of 15 degree, let's say, you get this, and alpha turns out to be 0.32, which is less than 1. So you're right, and you have k is 18.7. But the thing is, the 0 is kind of uh, close to the imaginary axis, so the dominance may not be achieved. It's not exactly dominant that you need it. So here you see the 0 is at 0.58 and the pole is at 1.79. It's not exactly dominating, right?
Yeah.
So that's what is happening here. See, there's a mismatch between the orange is basically system response if only the dominant poles are there.
Yeah, yeah, yeah. So the thing is, see, where I am worried is, in the exam we would not be having access to these computer generated plots and all. So we'll be having limited knowledge of the function with respect to that, the graphs and all, because we won't be able
What
to plot.
what you will do is probably draw a root locus, give the root locus sketch, work out some intermediate steps already, and tell you what is the right next step given what you want, like that. It'll all be conceptual, okay?
Yes, sir. I completely agree. That ways we'll be able to figure out. But what I don't understand still at this point is, I even took a look at the question paper of last term. What questions can we actually expect? I mean, the concept and all is clear for the most part. Now that you have explained it, but so what will the questions look like?
It'll all be simple questions only. I'm telling you, no. This is just for your assignment and your real life application, okay? Exam will be testing only conceptually, okay? Not on we don't ask you to uh, work out all these things, lengthy stuff.
Right. And for a lag compensator, I'm assuming we'll just add a differential term. Right? My
Integral
bad.
term.
Yeah, yeah, an
Okay.
integral term.
So now you choose gamma 55 degree, which is higher value. You get now this. So this is comparatively okay. The 0 is at 2, the pole is at 5. So not bad. So you see it is okay now. You choose this gamma is 41 instead of 55. Again you get this. Again you see it's not exactly matching. What you want to do is you want to choose gamma such that it maximizes alpha, correct?
Yeah.
So what you want to do is so alpha is ZC by PC, which is if you look at the property of this triangle, Wait, I'll show you. Alpha is this length divided by this length, correct? Correct.
Sorry. Which one? Alpha is.
Alpha is ZC by PC. So this length OZC divided by OPC.
Yes.
So if you do calculate that using the trigonometric ratios, sine law, cosine law, and all for triangles, what you get
Yeah,
is
the formula,
basically
right?
this. Yeah.
Yes.
And if you substitute d alpha by d gamma equal to 0, you get gamma is 41.53 degree. It turns out this is the best you can do. You can't do better than this.
Also, sir, the formula, what is it used to calculate actually? So, if you open the figure once, here we used the formula to calculate gamma, alpha, right? No, the other
Which
graph that had the angles. Yeah, precisely this one.
Mhm.
So, alpha wasn't given in this one, right? Which angle did we just compute?
Alpha is ZC by PC. I told you, right?
Oh, right. Oh, right.
So ZC is 1 by T, PC is 1 by alpha T. So if you divide ZC and PC, what do you get? Alpha, right?
So we wrote the lead compensator in this form, which k equals to. Once again, I'll just
Yeah.
note it down.
So if you know ZC and PC, you can know alpha. Sorry, you can know alpha.
Right.
So if you substitute SC equal to SD, you get SD plus ZC, correct?
Correct.
If you substitute SC equal to SD, you get SD plus PC.
Yeah, this is nothing but we are basically taking the angles.
So
So
this angle mu2 and mu1, if you so this if you phi is basically the angle that you want.
okay. Okay.
Phi
Just so
is
just
basically this angle deficit that the compensator needs to supply. Got it?
yes, sir.
And it turns out it is this. Geometrically, it is this.
Right.
Why? Because it is a difference between phi is a difference between two angles, right? Which is this minus this, right? You work
Hmm.
out the geometry, you get it. It's not a big thing. So this is SD, this is PC, and then this is ZC. These are three complex numbers. Once again, I'm charging my laptop. Give me a minute. So this part you see here, right? The angle of this guy is basically mu1. You see as SD plus ZC. The angle of this guy, SD plus PC, is nothing but mu2.
Hmm.
The difference of these turns out to be phi.
Yeah.
You're choosing PC and ZC so that the angle difference, this diagram, turns out to be phi. But there are lots of ZC and PC possible.
Correct.
So that depends on alpha, right?
Sir, by the angle deficiency is calculated by subtracting it from 180, right? I mean, this should basically be the angle G G of C should be greater than 180, right? Or 180. If it's less than
So
that,
if
then we have
the thing is angle of G plus angle of GC should add up to 180. You know the angle of G, which will be minus 170 or minus 160 or whatever. So the
Okay.
extra minus 20 will be the angle deficit phi that you see here. Got it?
G, oh yeah, G into GC, right? One is your, I mean, it's basically 1 plus
Yes, G
G.
into GC, but when you take the angle, they will add, right?
Right, right. Okay.
When you take the argument of a product is sum of the argument,
Yeah, yeah,
right?
yeah, yeah, correct, correct. So here we are just talking about the controller, that's all.
Hmm?
Here we are just talking about the controller, right?
Yeah, phi is I already know. Phi, you know what phi you want because you know the open loop transfer function. You know how much phi you need from the face of GC.
Hmm.
So substitute x is equal to SD plus ZC. This mu1 will be this, mu2 will be this. Subtract this, you will get this. Why? Because by a linear pair, this guy is 180 minus mu1, right?
Hmm. Right.
So, and the sum of these three angles should be sum of all three angles of a triangle add to 180. So, mu2, phi, and 180 minus mu1 should add to 180, which means phi is mu1 minus mu2, right?
Got it.
Or other angle is the exterior angle is sum of the two opposite interior angles. Another way of saying this, the exterior angle mu1 should be the sum of two opposite interior angles phi and mu2. So mu1 is phi plus mu2 means phi is mu1 minus mu2, correct? Which is the angle deficit that you need.
Right, right.
So this diagram is given to you. Once you know phi, you can draw this diagram and then label all these angles. Once you find mu1, mu2, you can label all the angles. Gamma is this angle. This gamma is basically this angle, okay? Got it?
Hmm. Yeah.
So now the thing is, higher the gamma, lower will be ZC and PC. If ZC and PC are closer, then what will happen to gamma? You can geometrically see. So now, just a moment. ZC is basically omega n. Omega n is basically this ratio, okay? And then if you apply the sine rule for a triangle, you'll get this sine gamma by sine of pi minus theta minus gamma. Pi
Yes.
minus theta minus gamma is basically mu1, correct?
Yeah. Yeah.
So sine gamma by sine mu1, okay? It's basically sine rule that you studied in school or college first year, okay? So one PC will be this. Now you have to choose gamma such that this alpha is uh, ensuring dominance of the pole of the compensator related to the zero, okay?
So can you scroll up once, please? Uh, yeah, I just wanted to see. Right, right, right. So ZC equals to omega n. Omega n is our frequency here. Right? Acha, okay, it's the same thing, right? Got it. That this we had already calculated earlier. We calculated this along with zeta, right? Yeah. Okay. Got it.
Everybody else, are you okay? Or are other people there or they left? Anybody else there on the call?
No, sir.
Oh, okay, you're only there. Okay, then it will just you who will decide the phase of. So now here, what you are ensuring is that choose your gamma such that it maximizes alpha because alpha should be as high as possible because when alpha is really high, ZC by PC will be, um, sorry, I think 1 by alpha. I think there is a typo here or something. I think alpha should be minimized, if I'm right.
Uh, if we divide each term by ZC, then it should be, I mean,
One second, one second.
alpha
Okay,
equals to something.
let me just take. I think I got stuck. Wait, let me just see once. So PC by ZC. Okay, PC should be much, much, much higher than ZC. Okay, the pole is to the left of the zero, so PC should be much, much higher than ZC. So PC by ZC should be much, much, much greater than 1. So ZC by PC should be much, much, much less. Yeah, sorry, it's correct only. I understand. ZC, this is obvious, right? I think then this should be alpha should be minimized. Alpha, I think this should be minimized instead of maximize. Anyway, it doesn't affect the first order condition. Whether you want to minimize or maximize, derivative has to be zero, right? It doesn't affect the rest of the analysis. So you do that and find gamma. That is the best you can get. Okay. Is this clear or not?
Yes, just one sec. I am just writing it down. Uh,
Do you have access to this presentation?
yes, sir, I do.
Okay. I don't know what happened to others. They ran away. It's 2 hours class today, right?
Yeah.
I don't know. They got scared or something.
Yeah, sir. I mean, most of us are this term at least. Because the syllabus is there's a lot to cover. That's why.
Okay.
Yeah, got it.
And then this is how you actually physically realize lag compensator. The thing is, on those days, the beginning of 20th century and the end of the 19th century, you didn't have any digital circuits or digital things. All your controllers would have to be realized by electrical circuits only, RLC only. So this topic was very important. How to realize physically a transfer function using analog devices. Okay.
Yeah.
So if you calculate the transfer function of this type of circuit, you will get something like this. So this is basically a lag compensated transfer function. So the T is 1 by RC, 1 by R1 C1, and the alpha is 1 by alpha is nothing but R1 plus R2 by R2. Got it?
Right.
Now let's go to lag compensator. Again, you start with this same thing. Um, yeah, pure gain turns out satisfies this. The root locus passes through this. But the thing is, the steady state error is kV is just 1 by 1 1. If kV is 1, what is steady state error? 1 by kV, which is 1, right? So, but let's say I want steady state error to be less than 0.1, which means kV should be greater than 10. So, which means I cannot do this anymore, right?
Hmm.
So that is why so even though the transient response specification is satisfied, the steady state response specification is not satisfied. One solution is just add integral controller, which will make it a type 2 system. And hence steady state error will be 0 for ramp, correct?
Yeah.
and then
Yes.
use root locus for this integrated system. Okay, and then choose the gain such that it passes through the poles that you need. Got it?
Yeah.
Okay. But the thing is, can we design a controller which improves the steady state performance without keeping the transient performance unaltered? What is the next question? So, but if you use an integrator, the transient response specification you have to rework again, right? The
What if
systems,
we add a pole and a zero?
yeah, that's where the lag compensator comes in. Okay, so
Okay.
in lag, so once again, so the lag compensator's job is, instead of putting an integrator and redesigning, you kind of put a approximate integrator that takes care of steady state without altering the transient performance. Got it?
So, sir, one second. In lead compensator, we just added an S plus ZC term, right? In
Mm-mm-mm.
compensator. That was it. That was simply a PD controller
Hmm.
and nothing
This is
else.
nothing but, see, in a lag compensator, the beta was, the alpha was less than one, right?
Yeah.
Here the beta is greater than one. That's the difference.
Right. But in the lead compensator, that is what we did, right? Just a PD
In the lead
controller.
compensator, you want to beat almost like a differentiator, which means you'll want a dominant zero and a faraway pole, correct? To
Correct.
realize here what you want is you want an almost integrator.
Right. With
So
minimum disturbance to the transient state. That is why we
yeah,
also to compensate that add a.
so that's why the
Uh,
beta should be greater than 1 year.
okay. Great.
You want an almost integrator here, so beta should be much, 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 much greater than 1. So that you will get S plus some very small number. So that pole of the lag compensator has to be really, 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 really close to the origin, while the zero has to be, really, really, really far away. So that it is almost like an integrator. Okay. Now the thing is again the same logic. Yeah, you find the angle deficit that you need. Correct. The thing is place ZG and PG such that the combined angle contribution is very, very low. Do you get the logic here? See, you want a pole and zero very close together so that their combined angle contribution is very low. It won't alter the transient response specification. Is it clear?
Yes, sir. Got it. Got it.
What is the error constant of this? Kv is limit s tends to 0, kgcg. So it turns out kv into zg by pg, which is kv into beta. So wait, the error constant of the lag. Okay, so you have beta is kv hat by kv, where kv hat is the desired velocity error constant, and the kv is the velocity error constant of the uncompensated system. So here the thing is when you put to compute kv, what you will do, multiply by s, that will cancel the integrator already there, and then put s equal to 0. Okay, so what will you get here? You will get the original kv of your system multiplied by zg by pg, right, which is beta. So your beta is, so this you know, you want the desired specification of kv, which is kv dash. Kv you already have, so based on that you can decide beta, correct? Do you agree or not? Beta.
Right, right. Yes, we can.
So based on the steady state error constraint, you can design beta. You can design beta. Once beta is computed, you have to choose ZG and PG appropriately. Of course, the beta just gives you the ratio of ZG and PG. Uh, the exact location is still not determined, right? So what you have to do is to if the reciprocal of ZG is tau, okay, write ZG as 1 by tau, and then you want the ZG close to the origin, and then compute PG, which is ZC by tau. So in lag compensator, what you do is, they have up an example here. Let me read this. Here, what happens is a gain of 8.25, a pure gain of 8.25, a pure root locus peak gain of 8.25 actually achieves a transient response specification. But it doesn't achieve the steady state specification because the velocity error constant is 1.03 and you want 10, correct? So beta is approximately 10, right? You want to put ZG and PG so that this transient part is okay, but and the whereas steady state part is improved. So what you do is you get beta equal to 10, and then choosing tau is you want ZG to be very close to the origin. So if you choose, let's say, wait, what are they given here? You're choosing ZG is zero point 0.1. Zero point 0.1 is much, much, much closer than 4 and 2 by orders of magnitude, right? You need a ZG that is very, very close to the origin. You need ZG and PG that are so close to the origin that it won't affect the angle. It don't affect the angle specification that you did for the transient response. Got it? Is it clear? See, in
Yeah.
lead compensator, you choose what? Where you choose ZC and PC for the lead compensator. You choose ZC and PC so that you mold the root locus to pass through where you want, right?
Yeah.
You have done the job now. Now you want to put an extra lag compensator for your steady state specification, which won't affect any of the design that you have done so far. So you have to ensure that those zeros and poles of the lag compensator are very, very, very close to the origin, so that their angles are the angle their angle deficit is contributed is much, much, much lower. Got it?
Yeah. Okay. Okay.
See, if ZC and PC are much, much, much closer to the origin than the other poles, all the other poles, practically you can take them as zero, right? For all practical purposes. Correct? Practically, it means practically there's a pole zero cancellation for all practical purposes. Compared to the other poles, the ZC and PC are coincident, and actually they're actually a pole zero cancellation.
Hmm. Right.
Okay, the logic is simple. If I put a integrator, it will eliminate steady state error, correct?
Right.
But I have to rework the transient response. It screws up the transient response plot. If you put a extra pole at the origin, it changes the root locus plot completely. So what you do is you introduce a zero that is very, very close to it, so that there is a pole zero cancellation. and so that it doesn't affect the extra root locus, the other part. Got it?
Hmm.
Okay.
Right.
So the root locus of the lag compensated system, it will start at the pole and end at the zero. There will be a very tiny strip only that starts at that pole close to the origin and ends at the zero close to the origin as well. If you want, I wait. I'll open a paint and show it to you. Give me a moment. It wants the moment. Wait a moment. It's hanging. Uh, I'll share my full screen now. Can you see the toolbox? So assume. Can you see my screen?
Yes, sir.
Assume this is your complex plane. Let's say. Okay, why did it change? Okay. Let's say you have this software original system. Okay, so okay, let me choose this. Let's say this was your original system, and your root locus originally it will be, let's say I'm just drawing a rough sketch. Okay. Uh, why is it so thin? Let's say it is something like this. It will be roughly like this, right?
Correct.
And let's say you have done everything, and this is actually where you want. This is actually very sweet spot for you. Okay. So you have done all the design and ensure the closed loop poles are like this. Now, but the thing is, this part doesn't satisfy a steady state requirement. So for that, a naive solution would be to put a integrator, okay, so that steady state error becomes zero, perfectly zero, correct? But putting integrator will change the nature of the root locus plot completely. Okay, I will use another color, light color. It will it will now be like this now. It will be so shitty and screwed up. It will be now like this. Something like this, right? I don't know exactly. It will be something like this.
Yeah, correct, 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 correct.
You have to do the design again.
Because then the concept of even number of odd number of poles plus zeros would come into play, and the entire
Yeah. So now what you do is to avoid this, you can also add a zero at the origin so that you have pole zero cancellation.
Oh, I see. So this is why we like. Okay, now that you do it graphically, now it makes sense why it's actually done that way.
But practically, it is not possible. Exact pole zero cancellation at the origin, it is not practically feasible, realizable, and it will also eliminate your steady state error. The steady state error will no longer be zero because the integrator is cancelled by the zero. S is 1 by S cancelled by S, right? So
Yeah, yeah.
what you do is you now place a pole very close to the zero origin compared to the others, and also place a zero that is even though farther with ratio beta is still these two are still much closer to the origin. So from the point of view of this faraway region, this is basically a pole zero cancellation approximately. If you see from very far away, two close enough points will appear as one, right? You see very far away, two close enough points will appear as one, right? Hello?
Yeah, that is right.
So
Yeah,
from the point of view of these faraway region, what is exactly happening here is actually a pole zero cancellation up here
yeah,
at origin. But it's not exactly pole zero cancellation because steady state requirements are satisfied without affecting the transient response. So the new root locus will be simply you will having another line here. That's it. That starts at close to the origin and ends close to the origin. That the remaining plot will be affected very little. It will be maybe slightly drift, but it won't change that much. Got it?
right.
So that is the logic of the lag compensator. Got it?
Right.
So beta should be really high so that the steady state error is controlled. But still, even if beta is high, these two together, have to be much closer to the origin compared to the remaining remaining guys here. Got it?
Hmm.
Can I now
Right.
go to the slides again?
Yeah.
So that is what is happening here. I don't know why they didn't draw that graph here. So here what happens is here they didn't show the other poles. That's why I think it's not clear. Correct? So one second, I'm charging my phone. So here the ZG and PG are actually different points. So there is no pole zero cancellation, and PG is very close to the origin. So the steady state error will be satisfying a specific edge. But from the point of view of the other poles, ZG and PG are actually close enough to the origin. There is practically there is a pole zero cancellation. It will look like that. Got it? So from theoretically there is so from the point of view of the dominant from the point of view of the dominant poles, it will be a it look like as though there is a pole zero cancellation. The remaining root locus plot will not get affected, but theoretically there will still be a dominant pole. There will be a pole and zero very close to the origin, making the steady state response controlled in the manner you like. Got it?
Yeah.
So that is where this design comes in. So you see here, you see a small part of the root locus here.
Yeah. It's a very slight shift.
Yeah. So this is the slight shift is due to the pole zero combination near the origin, but it's only slight because they are really close to the origin on each other.
Makes sense.
So the thing is, you use the lag. You first design the lead compensator and then control the transient performance, and then you design the lag compensator to control the steady state performance without affecting the transient performance. Okay,
Right.
so that is what is lead lag compensation. Okay, so if you use lead and lag together, you will have lead lag compensator. Okay, what you do is you design a lead compensator and then design the lag compensator.
Essentially, we are multiplying a zero that comes up for from our lead compensator, and then a zero and a pole again from our lag compensator, right?
Exactly, exactly.
Okay, okay. We were not. I mean, I don't know if the lectures went through all of this in. Maybe the terminology that was used was a bit, you know, uh, sort of hi-fi, because someone doing this for the first time may not make complete sense.
Okay, even I didn't I haven't even I haven't watched the lectures. I came to this course suddenly as a new instructor. So yeah, now it is clear.
Yes, sir.
The
Now,
terminology and the notations are off-putting generally in mathematical subjects like this. But yeah, the logic is actually simple if you actually look at the diagrams and reason out. It's not. Don't worry too much about exam. You don't get a design question. That's all purely for your assignments and for your practical application. If you go to an industry, and they use PD control or lag compensator, you have to know all these things. Okay, so but other than in your exams, you will kind of be focused more on MCQ type questions that shows that you have understood all the
yeah,
subtle things correctly. Got it?
yeah.
Okay, I'll stop the recording, and then if you want to